Hey everyone, welcome to our last lesson in Unit 6. Today we're going to finish up our lessons on bonding. Today we're going to be learning about covalent bonding. And by the end of today's lesson, you should be able to distinguish between nonpolar covalent bonds and polar covalent bonds. So two different types that we're going to focus on in addition to the ionic bonds that we had learned about in our previous lesson. So in covalent bonding, we're going to have two nonmetal atoms that attempt to gain each other's valence electrons. Remember, in ionic bonding, we actually had atoms that gave up electrons to another atom and became positive or negative ions. And that was with a metal and a nonmetal atom. But covalent bonding is going to require two nonmetal atoms, and they're going to actually try and share each other's electrons because they don't have enough difference in electronegativity to actually take them. So what that means is that either of the competing atoms that are trying to bond don't have a greater enough difference in their desire for an electron, so they end up just sharing the electron with each other. And the ones that are shared are going to be the unpaired valence electrons. And what's unique with covalent bonding, and this is what makes this bond really strong, is that the bonded atoms actually become part of each other. So these bonds are much stronger than ionic bonds. You know, ionic bonds, we can break that bond simply by dissolving the ionic compound in water or by melting it. But the covalent bond cannot be broken by dissolving in water or by melting. Therefore, what we call a molecular compound, something with covalent bonds, so covalent compounds will never conduct electricity like ionic compounds will. So they're not considered to be electrolytes. Now, in order to determine if a bond between two atoms is covalent, we're going to have to look at the electronegativity difference, just like we did with ionic bonding. Remember, the electronegativity difference with ionic bonding was higher than 1.7, and for covalent bonding, the electronegativity difference is going to be less than 1.7 to form covalent bonds. And in this scenario, the atom that has the higher electronegativity doesn't have quite the pull that it needs to actually remove the other atom's electrons. So instead, they share them. And what happens when this occurs, when they share electrons, each of those bonded atoms is going to try and achieve their stable octet. And after bonding, they will each have their stable octet of 8 valence electrons, except for hydrogen, which only has 2 valence electrons in its 2s sublevel, or excuse me, its 1s sublevel, which can only hold 2 electrons. So that's going to be the only one that's going to be less than 8 valence electrons. Now, this little chart here will kind of help us keep track of what type of bond we have between bonding atoms. And we're going to separate this into 3 different portions. And I'll try and keep this somewhat to scale here. Remember, the highest that this goes up to 4.0 and essentially down to 0. So we have something like this. And then we're going to have a line somewhere about here. And this first one we talked about in our previous lesson, 1.7 on our electronegativity scale. Anything greater than 1.7 is going to be an ionic bond. Anything less than 1.7 is going to be a covalent bond. And there's going to be 2 types that we're going to learn about. And there's going to be another separator here. And these numbers you're going to just kind of have to remember. But it's really only just the 2. So anything lower than 1.7 is a covalent bond. So if we're between 0.4 and 1.7, and we'll get more into this in a second, these are going to be polar covalent bonds. And if we're less than 0.4, from 0 to 0.4, this is going to be a non-polar covalent bond. So we have 2 different types that we're going to learn about. Both have electronegativities less than 1.7. And if we're less than 0.4, that's going to be our additional separator to separate nonpolar covalent from polar covalent. So this table will help you kind of keep track of the 3 different types of bonding that you're going to be responsible for. A little more about covalent bonds. They're really simple to remember. If we just break down the word, co meaning two, valent meaning valence electrons, or valence as in valence electrons, so we get two valence electrons, which means when we're talking about a single bond is going to be two electrons, a sharing of two electrons. And that's literally what it means. Now we can determine the number of covalent bonds that an atom can make just by looking at its dot diagram. When we write the dot diagram for any atom, we can see how many unpaired electrons that atom has. The number of unpaired electrons is equal to the number of covalent bonds that can form. For example, nitrogen has unpaired electrons at 3, 6, and 9 o'clock. Therefore, it can make 3 covalent bonds. Sulfur has 2 unpaired valence electrons, so it can make 2 bonds. Remember, we want to have a full octet of 8. Chlorine is missing 1 here at 3 o'clock, therefore it can make 1 covalent bond. This can also be indicated if we look at the group number. That's another way we can kind of figure out how many bonds a particular atom is going to make. Now, making molecules, we have 2 examples of molecules here, one being methane, the other being water. And what's unique about both of those is that they're made only from non-metal atoms. And those non-metal atoms are covalently bonded together. As far as molecules go, any molecule of a particular substance, let's say methane, and this would be what you're going to have in your homes, most likely, as natural gas. And we get into this in organic chem later in the year. Or you might be on propane as well, which is very similar to methane. But in either case, each molecule of methane or propane or water is going to be the same from molecule to molecule. And that tells us, or we have a formula here that tells us exactly how many and each type of atom that we need to make that molecule. So that's kind of how the formula is going to relate to that. Now there are 2 types that we're going to spend our time on here. 2 types of covalent bonds. Non-polar covalent bonds are going to create a molecule that does not, and this is the important part here, they do not have poles. Poles meaning charged ends. If you think of the poles on a magnet, like and unlike poles on a magnet. Unlike poles would attract, like poles would repel. Same thing here. In a nonpolar bond, in this case between 2 carbon atoms, carbon and carbon, we have an electronegativity difference of 0, and therefore it's the same pole for those electrons between each of these carbons. And therefore the electrons are going to lie about the same distance between those carbons all the time, as opposed to spending more of their time around one of the other atoms. And this doesn't create a positive or negative end. It does not create poles. In the hydroxide ion that we see here, we have a polar covalent bond. And in this case, the oxygen has a higher electronegativity and a greater attraction for the electrons than does the hydrogen. So electrons tend to spend more time around the oxygen atom. And that creates a pole, which is a charged end. So on this particular molecule, the oxygen end of the molecule is going to have kind of a negative charged end around the oxygen and a positive charged end around the hydrogen. So these are our poles. So polar covalent bonds creates a molecule that has charged ends or has poles. Whereas a non-polar covalent bond, since we have an equal pole for the electrons, does not create poles. The electrons spend an equal amount of time around both of those atoms. Now for non-polar covalent bonds, the electronegativity difference has to be between 0 to 0.4. And that's just saying that electrons are being shared equally. The difference in electronegativity isn't big enough for one of those competing atoms to actually take the electron or for it to spend more time around another atom than the other. And this is going to include all of our diatomic molecules. We don't really see C2, but we will see all of our diatomic molecules. Remember, that's Brinkelhoff that we have to write as diatomic, Br2. So that's a bromine bonded to a bromine. They have the same electronegativity, and therefore when we subtract those, it's an END of 0, which means that we have a nonpolar covalent bond, and the electrons in this bond are going to be shared equally between each bromine atom. We have no poles in that molecule because the electrons are shared equally. Now we can see here kind of with a dot diagram how we form these covalent bonds. In this case, they would be nonpolar. We have a bond with itself. In this case, for hydrogen, it's going to have the same electronegativity, so the difference would be 0. And we can see lining up that, remember, hydrogen only gets 2 electrons in its valence shell. We're missing one here, and we're missing one here. So the 2 hydrogens come together. They share their outer valence electron. And what that does, and we see it a little better with the oxygen underneath, each hydrogen now has 2 valence electrons. In this case, it would fill its valence shell. In the case of oxygen, we can see that each of these is missing 2, and therefore can make 2 bonds. And when these line up, remember, we want 8 for each atom. This is going to look like that. So when we circle each oxygen, there's 2, 4, 6, 8, and 2, 4, 6, 8 for each of those oxygens. And in this case, we have 4 shared, 4 unshared. And this, remember, a bond is 2 electrons, so this would actually be a double bond, and we would write that with 2 lines. And we can determine that by writing the dot diagrams. So I want to make sure that we're comfortable writing those dot diagrams. Now, polar covalent bonds are going to be bonds that are formed between, again, nonmetal atoms, but they're going to have an electronegativity difference from 0.5 to about 1.7. And we'll include 1.7 for the sake of argument. Anything above 1.7 is going to be ionic. But in this case, electrons are being shared unequally in the bond. Not enough for one atom to completely take the electrons, but enough where the electrons are going to spend more time around one atom as opposed to another. And it's going to spend more time around the more electronegative atom. And this is going to give the molecule a pole, a charge on either end of the molecule. Depending where the electrons are spending more time around the more electronegative atom, we are going to have our negative pole around that atom or around that end of the molecule. The less electronegative atom is going to become slightly positive because the electrons are spending more time around the other atom. Now, these charged ends of the bonds form poles, positive and negative, and that's why we call the bond polar, because it has poles or oppositely charged ends. And when we look at the case of hydroxide, oxygen and hydrogen together, we can see those poles there, and we designate those with a delta symbol, delta positive, delta negative, which is going to show our poles, which we're going to call dipoles. And we'll learn more about that in a future lesson. When we compare electronegativities, oxygen is 3.5, hydrogen is 2.2. The difference there is 1.3. That falls right in between our 0.4 and 1.7 number line. And therefore, this is going to be a polar covalent bond. And we can see where the electrons are spending more time by writing in the dipole. And that's going to go around. The negative dipole will go around the more electronegative atom. And the positive dipole goes around the less electronegative atom. Now, remember, in covalent bonding, an atom's unpaired valence electrons pair up, and the atoms actually become part of one another. The valence electrons of one bonding atom are shown as dots, And the valence electrons of the other bonding atom are shown as circles. This helps us kind of keep track of the electrons as they're bonding and making sure that we're writing these correctly and just kind of showing which electrons are coming from which atom in the bond. Now, this particle that gets formed from the covalent bond is called a molecule. Remember, they can only be made of nonmetal atoms bonding to each other. Now, a little more withdrawing here. We have a hydrogen and a chlorine. We can see that hydrogen wants to fill its valence shell with one electron, and chlorine also wants to fill its valence shell with one electron. Therefore, each of these wants to make one bond. They do that here, and it forms a single polar covalent bond. Looking at the example below, nitrogen is going to want to make 3 bonds, having a configuration of 2,5. It's going to want to increase its valence shell to 8 by bonding and achieving or obtaining in some way 3 electrons. And it's going to do that by bonding with 3 hydrogens, because each hydrogen wants to make 1 bond. And by drawing the dot diagrams, we can see how these are going to line up. And therefore, nitrogen is going to make 3 bonds with each hydrogen, and it's going to make a molecule known as ammonia, NH3. So we can see from our electron configuration how many bonds we need to make, and we can start to see how that is starting to lead us into our formulas. A couple more fine points about covalent bonding. When these atoms bond and share their unpaired valence electrons, the newly shared pair of electrons is going to form a molecular orbital, which actually belongs to both bonded atoms. This is created when the bond forms, and it is very strong, which makes these bonded atoms part of each other. And this makes that bond very difficult to break, especially when compared to ionic bonds. As we said, we can break an ionic bond simply by dissolving the compound into water or melting it. That's enough just to break the ionic bond. But covalent bonds cannot. If we think of, and I'll just kind of do something real quick, let's call this a sugar. If we were to try and dissolve a sugar into water, where you have a bunch of carbon and oxygen and hydrogen bonds here, these carbons are not going to separate from each other, or the carbons from the oxygens in the sugar molecule, like it would if it was ionic. This is going to stay as a whole molecule. It might get smaller, but it is not going to break apart. And that's because the covalent bond that's holding the carbons and the oxygens and the hydrogens together is much stronger than the ionic bond, and therefore is not going to break when it's dissolved or melted, and therefore will not conduct electricity. Now, the last thing here is IMAFs. I will often refer to this as IMFs, which are intermolecular forces or intermolecular attractive forces. And these are going to be a little bit different, and we get into this a lot more in later lessons, but this is different than the attractions inside of a molecule. What we're looking at here with IMAFs are the forces in between molecules, something like here, where we have a force between a negative portion of water, the oxygen atom in a water molecule has a slight negative pole, and it can line up with a slight positive pole from the hydrogen on another water molecule. And this creates an intermolecular force. And this, in this case, is what we call hydrogen bonding. It is a very strong type of dipole bond, and it occurs between molecules, not in the molecule, but between molecules. And this is responsible for surface tension on water. That's why the meniscus forms inside of a graduated cylinder, because we have this attractive force between the water and the edges of the glass container, which causes it to kind of creep up or walk up the sides because of that attractive force. It's also what allows an insect, I always think of water spiders, to kind of stand and walk on water. The force of that insect isn't strong enough to break through the water because it's weaker than the bond between all of the water molecules. And that's what allows insects to be able to walk on that water, and it's responsible for numerous other things which we'll get into in the future. If you guys have questions, make sure you write them down and come see me for help. Have a great day.